Okay, this is Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to EE21. So today's lecture will be the 16th lecture. And in today's lecture, we're going to continue talking about what we've started last time, which was energy storage elements. So if you recall, all of what we've covered previously was resistors. The passive circuit element that we've covered is actually only a resistor, and the resistor is a circuit element that dissipates energy. And last lecture and in today's lecture, we're going to continue talking about. We introduced the notion of two circuit elements. One is called inductor. The other one is called capacitor. So we're going to talk more about capacitor in this lecture. And we stated that these circuit elements, they are passive elements, but they actually store energy. Okay. Before we start, let's go over a few announcements. Homework 2 is posted and due this week, inshallah, on Thursday at 11:59. Please use the Gradescope to submit the homework, and by this time everybody should be familiar with the Gradescope. As far as the quizzes, quiz 3 has been postponed to Sunday based on the vast majority of votes, and it's going to be the same coverage, so 4.5 to 4.11. Please do not expect me to grade it immediately, so I will post the solution after the submission deadline. Okay. Going over what we did last time, so we stated the difference between a DC and AC power. We said in a DC system we have a current or a voltage that's constant with respect to time. An example of that is a battery. The AC power is something that's alternating with, it's called alternating current. It's short for alternating current, and it's something that's actually changing with respect to time. An example of this is the power supplied by the electric company. Also, we introduce inductors as one circuit element that we're going to heavily use in the following lectures. And we stated that the inductor is an element that stores magnetic energy. So we saw the relation between the voltage and the current. And the inductor, we stated that the voltage is, this is the inductor. Then the voltage is related to the current by the following differential equation: V equals to L di by dt. Or if we are giving the voltage and we're asked to find the current, we need to integrate. And we derived also the power expression. The power expression is very simple. It was derived from the fact that power is voltage multiplied by the current. And finally, we concluded with the definition of energy, and we saw that the energy can be simplified. The expression for the energy of an inductor can be simplified to the following expression. Okay. In this lecture, we're going to talk about another passive circuit element. Also, like it's a circuit element that stores energy, but instead of it doesn't store magnetic energy, it stores electric energy. But before studying capacitors, let's actually classify currents. So we're saying like we've been using the word current since the beginning of this lecture of this course, and as a matter of fact, we're referring to one type of current here. All the currents that we discussed is a single type of current, and this is called the conduction current. In reality, there are three types of current. The first one is the conduction current. This is the current what we discussed, This is the current that flows in conductors. If you have a wire and you connect a wire to a battery, and this is the current that's going to actually flow. Another very useful, very fundamental, and honestly is one of the key factors for this digital for this digital era in the history is called the displacement current, and the displacement current is actually predicted by James Clerk Maxwell, and this current is actually flowing in dielectrics. An example of this is the current that passing through a capacitor. If you have a capacitor, and the capacitor usually has two plates. Between them, there is a dielectric. When you say dielectric is an insulator, I mean dielectric is an insulator. And if you apply a time varying voltage, you will see that a current is flowing into the capacitor. And this type of current is not conduction current because there is no conductor here. It's something called displacement current. And also, this is the current carried by electromagnetic waves. Because if you are going to send an information from one point in space to another, you don't have like okay. Can you mute yourself? Okay. You don't have a line that connects this point, so you don't have a cable from the power station or from the base station to your cell phone. They are all connected wirelessly, and because of the information is carried through the displacement current. The last part is the convection current, and the convection current is a current that flows by mechanical mean, meaning that, remember, the current is a flow of charges. So we have, if you take one charge, if you take a group of charges, then you move them from one point in space to another. Imagine that you have a bag of charges. It's not something doable, but imagine that you have a bag of charges and you move them from one point to another. By the definition of the current, you're doing this is a current because charges have moved from one point in space to another. And an example of this is a cloud carrying charges that move from one point to another. In this lecture, on this course, we are interested in these two, and the conduction current and displacement current. Hassan?
ايوه دكتور، بسأل الحين الشاحن اللاسلكي هذا النوع هذا تو من فترة طالع، هذا يعتبر displacement current ولا؟
Yes.
Okay.
It's actually near field. It's a near field power transfer.
Okay.
Very good. Wait. Okay. So capacitors is a circuit element that we're going to study in this lecture. And the capacitor is formed when you have two conductor plates separated by the electric or insulating material. Remember, we have three classes of materials. We have conductors, dielectric, and semiconductors. Because there's a separation between there are two plates, and these two plates are separated by an insulator. So charges cannot travel between two plates. Again, here we're assuming ideal insulator. So when we apply a time varying voltage, charges can actually place themselves can displace from one charge can displace from one plate to another. Because of this, when we say that when you apply time varying voltage, what do we mean by time varying voltage? It means like an AC voltage. So you notice here, current will be, we will have a current if we have a time varying voltage. If we don't have a time varying voltage, then we have plates, and between the plates is conductor. So this means that capacitors behaves like an open circuit at DC. So remember back, we said like inductors at DC, they look like short circuit. For capacitors, they look like open circuits. Here I is 0, here V is 0. Also, the last thing that we're going to say about capacitors is they store electric energy. So any question about this? Any question about these information? Karim?
Yes, Doctor. When we say store electric energy, does it mean like a battery that energy can be supplied later as a battery?
Yes, capacitors, as a matter of fact, hold on a second, let me just. As a matter of fact, capacitors are used as a battery bank. So, yeah, they're used as a battery. Hadi?
Doctor, in the capacitor, when there is a DC, it's a power supply DC voltage. It acts like open circuits.
Yes.
Right?
Yes.
Then how's that possible? Can you explain it?
Well, let's see. If I tell you, if this is a voltage source, I need you to interact with me, Hadi. Okay. If this is a voltage source, and I'm asking you to find V naught. So what is V naught?
It's the same.
It's Vs, right?
Yes.
If I tell you that I have a capacitor, and let's go here, and in this capacitor, this is a conductor. This is also a conductor. And the one here is actually dielectric or insulator.
Okay.
Okay. So if you have this situation, so what do you think about the current? Will be any current flowing from this plate to that one?
By logic, no.
Okay. It doesn't have to. It's actually no current is going to flow. So that's why if you have a DC voltage, we'll have no current. So if we have no current, it means that it will behave like an open circuit. However, the situation is not exactly the same when you have an AC voltage. So when you have an AC voltage, so the AC voltage can actually, or the AC current can go from this plate to another. Okay.
Yes.
Okay, good. Very good. So an example of a capacitor is probably you've seen it in Physics 102. I don't know if you've. I doubt that you did an experiment on that because of COVID-19. So, but I believe there was an experiment for capacitors. And one common example of a capacitor is a parallel plate capacitor. So for the parallel plate capacitor, we have the capacitance is So A is the area between, or the area of each plate. D is the separation between them, and epsilon is the permittivity of the material, which is a property, an electric property of the material. We will not talk about it in this course. You're probably going to cover it in Physics 305. Okay, this is just an example. You see capacitors everywhere. If you check any motherboard and fridge or whatever, you see like some capacitors over there as well. Okay, back to Hassan.
دكتور الباتري يعتبر كاباسيتر ولا؟
Capacitor can be a battery, but some batteries they have some chemical means of creating of transferring energy from chemical energy to electric energy. But you can use a capacitor as a battery, so you need to charge it, and after charging it, you're going to use it. You're going to discharge. After charging it, you connect it to the external circuit, and it will behave like a battery. Okay, from a circuit perspective, the symbol for a capacitor is this one, and we're going to use the passive sign convention to express the current in terms of the current, to express the relation between the current and the voltage. And we see here that the current is given by the capacitance multiplied by the derivative of the voltage with respect to time. In reality, in practice, the unit for capacitance is farad, but in practice, you will not see anything of like, say, like 1 farad or 10 farad. You will see something very small, 10 to the negative 6 micro, or 10 to the negative 6 farad, or 10 to the between 10 to the negative 6 and 10 to negative 12. The reason for that is you need to actually play with the dimensions. If we go back here, you need to play with the dimension, and eventually you will see that your actually capacitor is huge. So that's why you have we use like very small values of the capacitors. Okay, since here we have a derivative of the voltage with respect to time, the voltage across the capacitor cannot change instantaneously, much like the current through the inductor. So the current through the inductor cannot change instantaneously. The voltage across the capacitor cannot change instantaneously. Okay. So now we know the current in terms of the voltage. What if we given, instead of giving the current, we're given the voltage? Instead of giving the voltage, we're giving the current. So you want to express the voltage in terms of the current, and we can do the same. We can use the same approach like what we did in the as we did in the previous lecture to derive the current in terms of the voltage for the inductor. So here we'll do the opposite. So if I multiply both sides by delta t or by dt, I will get CdV. So I integrate both sides, t naught to t, I d tau, therefore V of t is 1 over c t naught t I d tau plus Vt. Okay. So now we derive the voltage. What about the current? What about the power? So the power again is P equals to I multiplied by V. So this implies that P equals to C, which is the definition for the current. Remember, the current is C dV by dt. C V dV by dt. The power is the derivative of the energy with respect to time. And if you recall that the power is also C dV by dt. So if you multiply both sides here by dt and integrate, we will get energy equals to C So we can see here there are some similarities between the definitions for the inductor and the capacitor. So if you recall, for inductor, we have V equals to L di by dt. Here we have I equals to C dV by dt. For the energy for the inductor is actually W equals to 1 over L multiplied by I squared. Here we have W equals to 1/2 C multiplied by V squared. Okay, so let's solve this exercise. And it's somehow exactly similar to the exercises that we solved. But in this case, we're instead of having an inductor, we're going to have a capacitor. Okay. So we're given the voltage across the capacitor. So the circuit will look like the following circuit. And this one is 0.5 microfarad. This is Vt. So we have a voltage pulse here. So what we are asked to do is we are asked to derive the expression for the current, the power, and the energy. So probably the best approach to do this is to actually subdivide the interval into 3 subintervals. So we have from 0 to infinity. So we need to subdivide it into, we need to divide it into 3 subintervals. So the first one is for anything less than or equals to 0. The second one for from 0 to 1. And the third one from 1 to infinity. So let's start with, well, actually, let's solve each quantity individually. Because this is not that complicated. So given the voltage, can we find the current? Okay, let's see. Rahim?
In the first interval, since the voltage is 0, then the current is 0.
Okay. The second interval.
The second interval, it will be 0.5 microfarad times 4.
Okay, which is 2 microfarad.
Yes.
Okay. The third interval, you need to do some sort of a derivative, so I'm not expecting you to do it now. So we just write the answer. Takes. And you can see here that I remove the equality, because there is a jump discontinuity here. The current changes instantaneously. This is okay for the current, but not okay for the voltage. Okay, excellent. Okay. What about the power? Ahmed Al-Hamad?
It's CV times dV over dt.
Okay. There's a shortcut here. You have the definition of I, you have the definition of V.
Yeah.
So you can just multiply them. The first one is clearly 0.
The second one is 2.
The second one is you have 40 multiplied by 2 micro, which is 8. And the third one is you have this expression multiplied by the current expression, so this can give you minus 8 E. Okay. So now what about the energy? Energy is simple. Salman?
Yes, half C V square. So C is half also, and V in the first one is 0, and the second one is 4T. So it will be 1 over 4, 16 by T square.
Okay, so V square is going to, so the first one is correct 0. The second one is you have C is 0.5. So 0.5 multiplied by 16 is 8. And you have another half. Yeah, so it's going to be 4.
4T square.
Microjoule.
And the third one.
Third one will be 16 multiplied, again it will be 4. Okay. So now we derive the expressions for the voltage, for the current, power, and energy. So the next part is asking us to sketch the voltage, current, power, and energy. Again, I'm not going to draw them, so I have them here. So we can see that there is an abrupt change here in the current, and this is also apparent in the power. Okay. The third part is asking us to specify the interval of time when the energy being stored in the capacitor. Okay. Probably the best way to look at it is to refer to this figure. Let's see, Ziad.
Yes, so we can either get it from the power when is it positive or when the energy is increasing. And they both end at 1, from 0 to 1. They're stored.
Okay, exactly. So energy stored okay. I believe the fourth one is asking you to specify the interval of time when the energy is being delivered by the capacitor. And Yasser, not Yasser, Abdullah, Abdul Ilah. Ilah. إله. طيب ياسر.
Yes. So energy from 1 to infinity. The energy is being delivered.
Okay.
Because power is negative.
Okay, very good. The fifth part is asking you to integrate from 0 to 1, integrate the power from 0 to 1, and integrate the energy from, or integrate the power from 1 to infinity. So in this case, what should we do, Abdulaziz Al-Ahmadani?
So from 0 to 1, integration of the power will be the curve under the power curve from 0 to 1.
Yes, we can do that. This is an excellent way of looking into it. But the other way around will be, or the other interval from 1 to infinity will be hard to do by looking to the area under the curve.
So we can take the equation.
Okay, we can do it for both, but yes, you can. For example, here it's 1 multiplied by 8 divided by 2. This is going to give me 4 microjoules.
Yes.
Which is again exactly for the other one from 1 to infinity. We're going to take the expression okay. Very good. So let's move on to another exercise here. And in this exercise, we have an uncharged capacitor is driven by, yes.
So for this curve, is it for one circuit?
Yes, it's one for one circuit because you're varying the source.
So can I say
you're playing with this one?
Okay. So when we found the energy from the positive curve, can we say that the energy of the curve under the T t-axis is the negative
It
of
it
what we found.
it has to be.
So do we need to calculate it, or do we need?
No,
it's
in this case it has to be, because we have we are connecting with a voltage source, so the current has to die, and yeah, it has to be. But you need to actually to calculate it to make sure, because in some situations the energy will be saturated. You'll have constant energy, and this is what will happen in the next example.
Very clear.
Muhammad.
So, Doctor, in the last part, in part 5, can we just directly substitute in the equation of the energy that we already found, since the integration of the power equals the energy?
You need to take the no. In this case, you're asked to find the energy from 0 to infinity. So you're asked to do it over interval. That's one thing. The other thing is you're asked to actually solve to evaluate this integral. But here, if you substitute, then you will get the value of the energy at a specific time instant. You will not get it over an interval. واضحة؟
اوكي واضحة شكرا.
Okay. In the second طيب questions ولا participation?
Question.
طيب okay, go ahead.
What's the reason for the graph is behave like it's increasing, then reach the maximum point, then start decreasing again?
The reason for that is actually the voltage source. This is the same pattern as the voltage source.
Oh, okay, thanks.
You're supplying a voltage source, then kind of like removing the voltage source. So if you plot the voltage source, it's something like this. So what's driving the circuit is the voltage source, which is this one. You can see the energy is following the voltage source. Okay.
I got it. Thank you.
Okay, good. If we have in this exercise, we have an uncharged capacitor, something like this. And this capacitor is driven by a triangular current pulse. So we have a current source connected to the capacitor. So the value of the current pulse is given by this formula. So we're asked to derive the expression for the capacitor's voltage, power, energy for the 4-time interval here. So again, we have 4-time intervals where we should find the voltage, the power, and the energy in these intervals. Okay, let's try to do that. بجنيد.
اي دكتور نضرب اول 1-0.
Okay, let's start with
الفولتج اول انترفل.
Okay, so let's do it interval wise. So for t less than 0, v will be 0. What about p?
البي في ضرب باي 0 كمان.
And the energy will be also 0. So everything is 0. Okay. Now let's move from let's look for another one. بعقيل.
Yes, Doctor.
Okay.
For zero, between for T between 0 and 20,
Okay.
the voltage will be 0, also the power and the energy.
No, we have a current here. So the voltage will be, remember, 1 over C,
Sorry. Yeah.
T naught to T, V d tau,
Yeah, right.
plus, I'm sorry, I, this one should be I. So T naught here is 0. So the voltage will be what? It's 0.2 micro, so 0.2 micro from 0 to T. I is 5,000
tau.
V, in the previous case, the initial value is 0.
0.
Okay, so the voltage will be 12.5 times 10 to the power 9 T squared volt. The power will be simply the multiplication of the voltage with the current.
Yeah.
Yes. And the energy will be 1/2 CV squared. If we do it, we're going to get 15.625, 10 to the power 12, T to the power 4. The unit is joule. Okay. Let's check the third interval, which is 20 micro to 40 micros. Let's look for طيب عبد الله الجريري. So let's start with the voltage. Abdullah?
Oh, yes.
Let's start with the voltage.
The voltage will be 40.
Okay, the voltage will be, so the expression for this is going to be 1 over the value of the capacitance. So what is T naught here?
Between 0 and 1.
No, what is T naught? What's the initial time instant?
So 0.
Okay. Not really, Adnan.
From 20 to 40.
Okay, the initial value is 20. 20 micro, but here we are looking for finding expression. So this one should be T. So this one should be 0.2, which is the definition of the current. Plus V at 20. So this one, we need to go back to this equation and substitute. Substitute at T equals to 20 micro. And if we do this, we're going to get 5 volts. So the voltage will be 10 to the power 60 minus 12.5. For the current, for the power, will be again the cream. I multiplied by B.
I multiplied by B, so I'm just so it's gonna be the B and divided plus B.
I believe this one is 5. For the energy is going to be 1/2 CV squared, and it's going to be 15.625. The unit stream. Okay, we see that it's not that complicated here. So now let's find the last interval here. So in the last interval, it's a tricky one here. So for t greater than 40 microseconds. So what is the voltage? What is the voltage, Shabab?
V naught from the previous interval.
Exactly. So the voltage will be V naught, which is happens to be 10 volts. So we have constant voltage, as you can see here. The power will be 0 because we have the current is 0, and the energy will be 1/2 CV squared. It's going to be 10 microjoules. So you can see here that throughout the whole interval, the capacitor is actually storing energy. So the third part is asking you, why does the voltage remain on the capacitor after the current returns to 0? So when the current returns to 0, this one will behave like an open circuit. So the capacitor will still have will still have a constant voltage. Will still have a voltage. Why is that? Because you can see here that charges are actually trapped. So we are charging the capacitor, and there is no way for the capacitor to discharge. So charge will accumulate across the plates of the capacitor, on the plates of the capacitors. So whenever there is a chance for those charges to discharge, or for the capacitor to discharge, then the voltage across the capacitor will drop. Okay. Very good. So now let's cover the last part of chapter 6, and this last part is concerned about combination of capacitors and inductors. So what happens if we have not only a single capacitor or a single inductor, we have multiple of them. So let's start with the case when we have inductors in series. So let's imagine you have the following. This one L1, L2, L3. Let's say that the voltage, this one is V1, V2, V3, and the current passing through them is actually I, because they are in series, so they must have the same current. And what is the voltage here? V. So the voltage here, V, is going to be V1 plus V2 plus V3. So what is the voltage across an inductor? It's actually L. V1 is L1 di by dt plus L2 di by dt plus L3 di by dt. So we can take di as a common factor, and we'll get L1, L2, L3 multiplied by di by dt. So this one is called equivalent inductance. So if we have inductors in series, then the equivalent inductance of those is this one, where its value is L1 plus L2 plus L3. أحمد نافع.
يعني دكتور بهذه الحالة ال V equivalent أقدر إني أجمعها.
Yes.
على الرغم من إنها series in series.
V equivalent. No, if this point is A and this point is B, then you can model it like this.
Okay. Thanks.
So you can see here that if we have inductors connected in series, then the equivalent inductance will be the summation of the inductors of the individual ones. Ziad?
Can we use a voltage divider and put the when we want?
Yes.
Okay.
Okay, good. For inductors in parallel, we have the following situation. So this is I1, I2, I3. So they have the common voltage. The voltage between them is common. So if you apply KCL, you will see that the equivalent inductance is given by this formula. And since here we're applying KCL, so we're looking for the current. And if you recall, well, the current is across an inductor is going to be so T naught is going. The total T naught will be the summation of the individual ones. So in conclusion, inductor combination is like resistor combination. If they are in series, you add them up. If they are in parallel, you take the parallel combination or the harmonic mean. Okay, what about capacitors? The situation for capacitors is a little bit tricky. For capacitors, if they are in series, then you actually the equivalent is something like this. The derivation actually in the book, I'm not going to go through it. And the summation of the individual ones, the initial voltage will be the summation of the individual ones. So capacitors in series, their equivalent capacitance is less than the individual ones. For capacitors in parallel, their individual capacitance is actually will be the summation of all of them. So in conclusion, capacitor combination behaves opposite to resistor combination. Okay, any question? Okay, we will not do an exercise of this one, but it's actually if you go to your book, you see like a bunch of exercises over there. So I encourage you to go over there and solve these exercises, because there is nothing fancy about those. You treat capacitors in the opposite manner that you treat inductors and the resistors. So any question before we move to the following part? Okay, this is good. So what we've covered so far, so let's let me just review what we've done in this course. So we started with definitions for voltage, current. So we started with voltage, current, power, and energy. Then we moved to Ohm's law, KVL, KCL. Then we talked about combination. So at that point we said, well, we have everything we need to solve any resistive circuit. But we noticed that in some cases we have complicated circuits, so we spend very long time on circuit analysis. Then we said, well, that's enough about DC. We've mastered almost every aspect of DC. So let's introduce two circuit elements that are going to be very useful in our analysis. So we introduced inductor and capacitors. Remember, our ultimate goal is to consider AC analysis. But from here to there, there's some very important topic that we need to cover. So what happens if we just connect the battery? So the original assumption that we use is actually you connect the battery, you have constant immediately. At 0 instant, you will have constant voltage or constant. You connect the source at 0 time, you will have constant current or constant voltage, depending on the type of the source. But in reality, this is not the case. In reality, you will see there's some short time response that's very critical, because this short time response might kill your circuit if you don't design your circuit properly. So this is the goal of chapter 7 and chapter 8. Let's start with chapter 7. we're going to, I mean, the title is response for the response of first order circuits. This is the book, or this is the chapter title. So you may ask yourself, what do we mean by response? Well, we know capacitors store electric energy, inductors store magnetic energy. We know that capacitors can have initial voltage associated with them. Inductor can have initial current associated with them. So you may ask yourself, if we go back to this circuit that we've studied, we have a voltage, we have a constant voltage after, say, like 40 microseconds, 50 microseconds. So what happens if if I connect a resistive load to that one? If I have a resistor and connected all of a sudden to the capacitor, I said, like, when we explaining this, I said like there will be some sort of discharge. Okay. This is the type of response that we're going to study. We're going to study, say, like the voltage across the capacitor when we just connect a resistor, or the current across the inductor when we connect a resistor. And this is known as the natural response of RC or RL circuit. Another situation that might be very useful is you have a capacitor or inductor, you just connect a source. So you want to study immediately what happens in this few milliseconds from the time you connect the source to, say, like a couple of milliseconds. You want to study this, and this is known as step response. So in this chapter we're going to cover both the natural response and the step response. We're going to do the same for next chapter, but there are some differences here. Yes, you had a question?
No.
So let me just explain it here. So this is the natural response. You have an initial voltage or initial current, and the current will discharge when you connect a resistor. You have an initial voltage, and it will discharge when you connect a resistor. This is known as the natural response. The step response is you suddenly connect a voltage and an ideal voltage source. عرفنا resistance. So just a minute. So the discharge dissipate power and are equivalent. Here we apply sources to capacitors or inductor. They start charging and storing energy. Think about it this way: you have a power bank, and here you're connecting the power bank to your device. Here your power bank is dead, and you want to charge it. Okay. In order to analyze this type of behavior, we need to actually be familiar with something called differential equations of the cream.
I'm sorry, Doctor, I did not get the difference between the step and the natural.
The natural is you charge your capacitor or inductor, and then you connect a circuit element to it. The step is you have something not charged, and you start accumulating, you connect a source to it. Think about it as a battery, as a power bank, the battery power bank. So the natural response is what happens when you connect your cell phone to the power bank. The step response is the power bank is need to be recharged, and you connect the power bank to the power outlet, recharge. That's a difference.
Okay, clear, thank you.
So in order to study the behavior, we need to be armed with differential equations. Differential equations are actually in Math 201, 202, or Math 208. So depending on which curriculum you're following. And in this course, we're going to use differential equations to study the response of RL. What we mean by RL is a resistor it's a circuit with a resistor and inductor. RC is a circuit with a resistor and capacitor. And RLC is a circuit with a resistor, capacitor, and inductor. So what do we mean by differential equation? What are differential equations? So a differential equation is an equation that relates a function to its derivative. So let's, an example of this is if you have di by dt equals to say a multiplied by I. So this is an example of a differential equation. So you have a function which is I, and it's related to its derivative, which is di by dt. So differential equations have wide applications in science and engineering. An example of this spring mass problem, heat transfer, wave propagation. All of these are governed by differential equations. One important thing about differential equations is actually the order of these differential equations. So what do we mean by the order? The order is the maximum order or the power of the highest derivative. So the power of the highest derivative. Here, this one is first order. This one is second order. This one is third order. So in circuit analysis, if we have a resistor and a capacitor, or a resistor and inductor, then we will have a first order differential equation. If we have a resistor, capacitor, and inductor, then we'll have second order differential equation. So in this chapter, we're going to study first order differential equation or first order circuit, meaning that a circuit that has a resistor and a capacitor or resistor and inductor. In the following chapter, chapter 8, we're going to study second order circuits, a circuit that has a resistor, capacitor, and inductor. And you can see here, I will see inshallah in the next lecture, that if you write the voltage or the current, it will be something like this. You'll have the derivative of the voltage equals to something. In the next chapter, we see that, for example, the second derivative of the voltage is equal to something. So that's why we have the first order of this chapter, the second order of next chapter. Remember here we're talking about we have one or equivalent, meaning that if you have two inductors in parallel, then this one is still a first order because you can combine them. You can have a parallel combination of them, or two inductors in series. This is still a first order. Okay, that's it for today. Inshallah, starting from tomorrow's lecture, we're going to cover chapter 7, and we're going to start talking about the natural and hopefully step response of RL circuits. Any question?
Yes, Doctor. The midterm will cover until which section?
There's an announcement in the comment section until 4.30.
Okay.
Ahmed, yes.
Doctor, is there a help session for the midterm?
I will try my best, but I cannot promise anything.
Okay. Doctor, could you please send any message for if there is a help session or not?
Yes, I will not. I will not make it secret.
Yeah. Okay.
Okay. Any other question? Okay. See you inshallah tomorrow.